and thank you to the organizers for this invitation. I am Subhasish Maiti from ISA Pune, and do not get confused by the name. I am other Subhasish Maiti than the one spoke on Monday. So both are sitting in the same room basically. So today I will be talking about decoding the phase of reheating with the NANOGrav 15 years of data. So this work has been done in collaboration with Nilanjan Dev Bhowmik, Mohammad Riazul Haq, Devaprasad Maiti and Professor Shiram Kumar. So let me just briefly introduce like what I will be talking about, what's the motivations. So I mostly work on the epoch of inflation and the subsequent phase of reheating. So what's the inflation? So cosmic inflation is basically an accelerated expansion of the universe at very early stages. And one can show that this accelerated phase can be derived by a single canonical scalar field minimally coupled to gravity, where this is the potential, this is roughly the potential how it looks like. Now by far we have already seen this kind of potential many times in this seminar. So what I am interested in here, so let us see, this is the slower region. So what we need? We need sufficient amount of inflation, like roughly 60-fold. So this tells us that the field has to roll slowly down to the potential. Now during inflation, we know that we also have the perturbations generated naturally during inflation, which at the later time gives rise to various observables that we see today in the present universe. So there are scalar perturbations generated, there are tensor perturbations generated, where tensor perturbations are also known as the gravitational wave. What I have plotted here on the right side, so this is the 2-point correlation of the power spectrum, of scalar perturbations. Now on the large scale, we have observations of CMB that constrain our scalar perturbations over the large scales here on this. And the large scale corresponding to the modes which leaves the Hubble radius during inflation at the very early stages of the universe, inflation, and which constrain the early stages of the inflation like roughly 10 to 15 epochs of inflation. But the dynamics of the later stages of the inflation are still poorly understood. So there might be like scenarios where some non-trivial dynamics can be happened over the later stages. Now what particularly we are interested here is this kind of scenario, you can see there. So here we can see that in this region the potential of the inflaton becomes extremely flat. So in that situation what happens that the speed or the velocity of the inflaton field becomes extremely small, which is also refers to as ultra slow roll inflation. And this is kind of a model that just Ratu spoke about, the two slow roll region, and there is one ultra slow roll region that is sandwiched between two slow roll region. And this is very famous picture like to generate this kind of PBH and secondary GW. So what it does is that if we have this kind of scenario, we get that the power spectrum or the scalar power spectrum will have an amplification or have a large strength over the small scales, larger like almost of the order of at least 10 to the power 7 times larger than what we have on the CMB scale. Now why do we need this kind of power spectrum? Well, I just said that this kind of scenario actually is very important in the context of PBH formation and the generation of secondary gravitational wave, which I will be talking about in this talk. So before going to the analysis, let me just quickly tell you about what are the assumptions we have taken in our work, in this work. So we have considered that we didn't take any numerical power spectrum in this work, rather we have considered an analytical power spectrum which has a nearly scale invariant part here, and it has a rise of k to the power 4 kind of stuff, and then it drops as k to the power n naught. We have also considered that during reheating, the equation of state of reheating will be constant throughout the reheating, and the transition from reheating to the radiation dominated epoch is sudden. So with that, first let me explain what PBH is. You already heard, but let me just summarize still. So what happens during inflation, that all the perturbations grow and go to the super Hubble region, After the end of inflation, they re-enter the Hubble radius. And if we are talking about scalar perturbation, what it does is like they accumulates matter and create overdense regions. Now, if the density of these overdense regions become above some certain threshold or critical value, which I have quoted here, the region collapse and form primordial black holes. This is famous picture of known as base sector formalism. So let me emphasize that this form of the delta C analytical we have taken from this paper. I should also say that there are also uncertainties in the calculation of this delta C analytical, which we will also take into account in our later work. Now, once PBHs are formed, they are cold and non-interacting in nature. So they can act as dark matter. Now, fraction of total dark matter in the present universe is coming from PBHs, that is also what is known as this quantity FPBH. And if PBHs are formed during during reheating, this is what the form of FPBH will look like, where beta m is basically the abundance of PBH. Now, this quantity what I have plotted here for different parameter values. What I also want you to notice is the contour plots. So, they are basically the constraint on the maximum allowed value of FPBHs that is coming from various observations, and they are mass dependent constraints. So, with that, let me also move on to the spectrum of gravitational wave. So, yes, the dynamics of reheating will also have effects on the spectrum of gravitational wave for the modes that re-enter the Hubble radius during reheating. So, when we are talking about the gravitational wave, this omega GW is generally the quantity of observational interest, which is given by the ratio between the energy density of gravitational wave to the critical energy density of the universe. And this is the quantity I have plotted in this book, where dashed line you can see here is basically the omega GW for scalar the primary gravitational wave, which is basically generated from the metric perturbation without any source. And this solid line, which has this peak kind of nature, is the scalar induced secondary gravitational wave, omega GW for the scalar induced secondary gravitational wave. Now, also this red dashed line you can see here is basically a constraint for coming from delta n effective bound. So, whatever we do, we have to take care that it does not cross the bound of delta n effective. Now, this kind of all the primary or secondary gravitational wave, they are basically primordial in origin. So, they are expected to be present in our current universe as a stochastic gravitational wave background. Now, recently PTA has, of like a couple of years back, PTA have observed this kind of stochastic gravitational wave background. After the data released, there are multiple efforts to explain this data in terms of with the gravitational wave coming from various sources, where the scalar induced secondary gravitational wave remains a promising candidate to explain the data. You can see here. So, now most of the work that that contains to explaining the data in terms of the scalar induced gravitational wave face one challenge, major challenges. What is that? That for the power spectrum, the corresponding omega GW that satisfy the data which is generated during radiation domination, that satisfy the data, it leads to overproduction of primordial black holes. So, in this work, our goal was to explain the data with our model or the scenario, where gravitational wave is producing during reheating without leading to any PBH overproduction. So, to do that, we have run our analysis to compare our model generated the gravitational wave with the data. We have used the publicly available code PTRCAD. What we have first done, we fixed the temperature of reheating at a very low, which is 50 MeV, and we have run 4 analyses. And the first analysis, which is a 4 parameter free run, we have 4 parameters, 3 power spectrum parameter, which is the position of the peak, amplitude of the peak or the strength of the peak, and the spectral index of the decreasing part, and also the reheating equation of state. Now, after the first run, what we see that our analysis has a very weak dependence on N naught. So, in the next run, what we did, we actually, which is known as the 3 parameter free run, we fixed the value of N naught to -2, and we have run with peak, K peak, A naught and WRE, and we see that it kind of resembles this kind of nature in this plot. Now, till now whatever we have done, we haven't imposed any kind of any kind of constraints over on our run. So we expect that there might be the problem of PBH overproductions, which were our concern. So to overcome that, what we did, we mapped our variable from power spectrum variable to the variable of primordial black holes, which is the mass and FPBH. And in the third run, which is 3 parameter bound run, we run with M, FPBH and WRE, and what we did, the constraint was that FPBH cannot cross more than 1. And also in the fourth run, we have run with 2 parameter, which is M and WRE, and we have fixed the FPBH to the maximum allowed value here, the mass dependent constraints, we have fixed the FPBH to that. And after the run, we get this results. And also I want to emphasize that I have said that there are also uncertainties in the calculation of delta C analytical. So to take into that account, we have also run with 0.5 delta C analytical and 1.5 delta C analytical. And we see that for delta C equals to 0.5 delta C analytical, most of the allowed region like parameter space are omit because of the PBH overproductions. Okay. So this is the parameter based with parameter values that we got from our analysis. So let me just go through the results. So yes, this is the spectrum of omega GW using these base fit parameter values, and this is the corresponding FPBH. What you see that this green and red curves are corresponding to the runs, the first 2 runs, which are the free runs, which are there are actually the problem of PBH overproduction, where FPBH is greater than 1. You can see, which we have overcome with the next 2 runs, which are given in this red and blue curve. Now, how good is our model? We wanted to see. Our scenario is to do that, to check that. We also performed a Bayesian analysis compared to the astrophysical model, SMBHB model. Yes. So we saw that for delta C equals to 0.5 delta C analytical and 1.5 delta C analytical, we got a large base factor. So you can say that our model is well favorable. So with that, let me just summarize that. Yes, scalar induced secondary gravitational wave generated during the phase of reheating can satisfy the NANOGrav 15 years of data without leading to any problem of PBH overproduction. Thank you.
Thank you for the very nice talk. So I had 2 quick questions. So one is, in your model, can you introduce PBH spin?
We haven't thought of that. I think that can be done. I'm not sure like what extra we will get from that, because in this analysis our role was like our aim was just to see that whether it can explain the data without any overproduction. But I'm not quite sure if we include the spin of what modification we will get.
And the other thing is, so when you introduce this model, how fine-tuned your parameters are?
Oh, actually, okay, it's not that much actually. So there's no model actually. If you can see is that so we have an analytical power spectrum. So we have a range of parameters with which we have run. So that's all. So model you means the we need to construct a model like potential. We do not have a potential in this curve. Many can be constructed if we have the power spectrum.
Okay. Okay. Thanks.
Okay, hello. Yeah, generally in your model, the P curvature power spectrum goes k to the 4 when it's rising.
Yes.
Generally, gravitational wave proportional to P Earth square. Okay, omega GW is proportional to P Earth square with some integral.
Yes.
But NANOGrav predicts typically the spectral index of the GW around 2.
Yes. Yes.
So there is, but your curvature.
So this is around 2 actually. So if you
what is the physical reason that this scalar goes k to the nearly k to the k square, where your power spectrum typically goes k to the 4, your source term typically goes k to the 4,
yes.
Your GW goes k square. You get my point?
So, are you asking whether k power 4 is
power spectrum?
Yes. For this kind of scenario, generally source goes k to the 4.
So there is no analytical calculation. There is one very recently by the Chinese collaborator
Do you have a?
Yeah, that can be shown, and then if that's what you're asking.
Yeah, but the source is much steeper than the GW, no, in these scenarios. So there's suddenly
That depends on the transfer functions.
Etc. So this is the actual expression for this omega GW. It's very complicated to.
and it means it always goes get nearly square behavior, or it can be changed. Like
The most ultra-slower model, it is K-power 4 runs in the power spectrum.
but I am talking about the spectrum of the GW sourced by.
Imagine it, because it is ultra-slower models, it should also behave at the same time.
Oh.
But I need to check that.
It will change a bit, like if we have a different WRE, but it won't affect that much.
It will. I'm talking about radiation.
Radiation, okay. So,
I just no. What is the physical? Because source is goes K to the 4.
so he's saying that this
The
PR,
proportion of
this
GW
pro
is
PR
K
is K to the
square.
power 4, then why do we have
K square
omega GW
maybe.
that is K square?
Generally, in case of magnetic field, generally we have seen that they are the square of the NB, but in this case there is a difference of the spectral the nature of behavior. So
That should be possible to show.
Yes, yes.
Probably.
So I'll try to check that.
Yes. So Ashish, here.
Yes.
So that reheating temperature, is that quite low?
Okay. So why did you choose that?
Yeah.
Okay, let me just. So basically, we wanted that the corresponding mode that we enter the Hubble radius that correspond to the this NANOGrav band. So if we consider the reheating temperature that low, that's only when the K corresponding to the mode will lie somewhere around here. So we wanted our window that lies in the reheating epoch, window of PTA band. If you increase the reheating temperature, it will somewhere like around here or here. So that's nothing but calculating in the time of radiation domination.